For our reaction, we've got 2NO gas plus O2 gas in equilibrium with 2NO2 gas. And we can write an equilibrium constant here, Kc expression, NO2 squared over NO squared, O2 in the denominator, products of a reactants, and we're told that this value is equal to 6.9 times 10 to the 5. So for our conditions in part A, we're told that a 5-liter vessel is filled with some NO initial, which is 0.060 moles in 5 liters. Which will give us 0.012 molar. Also contains 1 mole of O2. This is 0.20 molar. And it also contains 0.80 moles. Sorry. This is NO2 initial, 0.80 moles over 5 liters. And this would give us 0.16 molar. Now from here, what we're going to do is we're going to calculate a trial value, a quotient, which is going to be equal to the molarity of NO2 initial. These are all going to be based on initial values, NO initial squared, O2 initial. We have all of these values. Let's plug them in, leaving out units, 0.16, 0.012 squared, 0.20, and we can solve here and we'll get 800 and to two significant figures, 890. We'll compare that to the actual equilibrium constant of 6.9 times 10 to the 5. So the Q, which is 890, is less than the equilibrium constant, 6.9 times 10 to the 5. So therefore the equilibrium, since the trial value, the initial values, are less is less than the equilibrium constant, we're not at equilibrium, and to get to equilibrium, the equilibrium shifts towards the right. For part B, we have another set of initial conditions here, and so let's calculate these values here. So we've got NO initial, which is 5.0 times 10 to the negative 3 moles in, again, a 5-liter flask. 0.20 moles of O2 initial, 0.20 moles per 5 liters, and NO2, we've got 4.0 moles per 5 liters. Let's work out these values here. This would give me 0.0010 molar. This would give me 0.040 molar, and this would give me 0.80 molar. Let's calculate our quotient, which would be 0.80 squared over 0.040 squared this should be 0.0010 squared, 0.040, and solving for the quotient, we get a value of 1.6 times 10 to the 7th. Let's compare that with the equilibrium constant. The quotient is 1.6 times 10 to the 7th. The equilibrium constant given in the question is 6.9 times 10 to the 5th. This time the quotient is greater than the equilibrium constant. Not at equilibrium, but to get to the equilibrium this time shifts towards the left when Q is greater than the equilibrium constant.